Welcome to this special episode of Frequency Matters, the RF and Microwave Update series. I'm Pat Hindle, and I'm here with Wang Johnson, Senior Vice President of Sales and Business Development at IQE. Welcome, Wang.
Thanks, Pat. Happy to be here.
So today we're going to take a look at trends and advances in high-frequency epi wafer technology. So as a major supplier of 3.5 substrates and epi wafers, what applications are the sweet spot for the various 3.5 materials and why?
Well, first of all, I have to say that silicon is a great semiconductor material. It's been transformative to modern life, and the continued advancement of silicon-based technologies, whether along Moore's law or in other device topologies, has just been an absolute testament to the industry. But Mother Nature always wins, and there's some fundamental limitations to silicon-based devices, which is where things become very interesting for compound semiconductors. So really, if I have to focus in specific areas for compounds, it's high frequency, high power, or light emission. And in some cases, it can be the combination of those where you might need high power at high frequency, for instance. There are just some fundamental materials limitations that allow certain compound semiconductor materials such as gallium arsenide, gallium nitride, or indium phosphide to simply exceed the performance attributes available from any silicon-based device.
So what trends are you seeing in the materials industry driven by fast-growing markets like 5G and Wi-Fi 6 and 6E?
Yeah, the most prevalent one is the push toward higher frequency. As we mentioned earlier, high frequency certainly favors compound semiconductor materials for fundamental materials property reasons. And 5G networks have utilized for the first time higher frequency bands in addition to the low and medium band frequencies used in previous networks. So the so-called sub-6 gigahertz bands represent a significant increase from the 2 to 3 gigahertz cellular frequencies of previous 2G, 3G, and 4G networks. This really places additional performance requirements on, for instance, the power amplifier in the front end of the RF chain. And compound semiconductor materials are very well suited to address those needs. In addition, as you look forward toward millimeter wave frequencies and deployments, these are frequencies that have never been used for commercial communications before. We're really borrowing here from military technology and phased array radars, where compound semiconductors such as gallium nitride have really carved out a particularly dominant market space. And then in addition to 5G, if we're talking about Wi-Fi 6 and 6E, what you're seeing there is also an increase in the operating frequency up to around 7 gigahertz or so. And so whereas you saw many of the Wi-Fi applications trending more toward silicon-based topologies at 2.4 gigahertz or lower frequencies, now up towards 7 gigahertz, you start to see gallium arsenide-based PAs become much more prevalent.
So I was thinking that, many design engineers probably don't realize the impact of the material structures can have on their device performance. Can you give us some examples of material structures that have been engineered to improve things like linearity and breakdown voltage, et cetera?
Yeah, certainly. One of the things that I like to describe to designers is that all circuit level problems don't need to be solved at the circuit level. And likewise, all device level problems don't need to be solved at the device level. And what I really mean by that is that using alternative materials or just intelligently engineering the underlying materials, you can actually develop solutions to many of the device characteristics that you mentioned, or several others as well. And in some cases, these can be a drop-in replacement to existing device architectures. And there are many examples. If I just pick a couple, if you take power electronics, for instance, switching from silicon-based power electronics designs to wide bandgap designs such as gallium nitride or silicon carbide can provide a much lower on resistance for a given blocking voltage, or alternatively, a much smaller chip size for a similar on resistance and breakdown voltage rating. And in both cases, the compound solution will typically provide improved conversion efficiency. In other areas, if we're talking about the RF space, changing individual layers, for instance, in a compound semiconductor device, take a gallium arsenide HBT for a power amplifier, for instance, you can change individual layers there in such a way that you can impact the linearity, the shape of the device response, and you can affect things like linearity or more second order subtle effects like performance versus temperature. There's a big periodic table out there, and the number of material solutions that can be used to address these types of device problems is very significant.
And I know you've been involved in some very interesting projects like 3,5 materials on silicon, dilute nitrides for HBTs. Can you tell us which projects you're excited about for the future of device technologies?
Oh, there's so many interesting materials projects, no shortage of compound semi materials. You mentioned dilute nitrides. That's a very interesting one. Dilute nitride materials are a special group of materials used to essentially change the wavelength, to engineer the properties of the semiconductor material, and specifically to reduce the band gap. And what that does is it allows for an optoelectronic device to shift the emission frequency or the detection frequency to longer wavelength. Now, why would someone want to do this? Well, take for example the 3D facial recognition that's prevalent in many high-end phones these days. Right, everyone talks about the notch and trying to get rid of the notch. Well, one way that one could envision doing that is by emitting at a longer wavelength and therefore being able to place those types of sensors below the surface of the screen. Another similar application for longer wavelength technology would be in automotive LiDAR, where the current operating frequencies of these systems is really not desirable for eye safety and for other reasons. And so pushing to longer wavelength is extremely advantageous. Another one that's really interesting these days is micro LED. And so if you look at all of the applications that we have for advanced displays these days, those are already very prevalent. But micro LED promises to really bring an entirely new topology to displays where you can engineer individual pixels with addressable content and with logic. And not even just the light emitter itself, but you could even envision having direct access on a pixel by pixel basis to sensing functions or communication functions. And all of that really is going to be enabled by the availability of the appropriate semiconductor materials grown at scale and with the appropriately engineered materials to enable those light emitting devices for the micro LEDs.
What new epi advances do you see coming in the near future that will enable engineers to improve their device performance?
You know, the really interesting thing that we see in the industry right now is really the beginning of the confluence of compound semiconductors with silicon itself. And that's really manifesting itself by the fact that the compound semi applications are growing sufficiently important that the volume and the scale that they're going to require is becoming comparable to what is available in many silicon factories. And so what I think you're going to see over the coming years are the traditional silicon fabs and foundries beginning to look much more closely and even process compound semiconductor materials down traditional CMOS fabrication lines. Now that's really exciting because one, it enables a size and a scale to manufacturing compound semiconductors that's really never existed before. But in terms of performance, inherently what you'll find then, if you have compound semis and silicon living side by side in the same factory and being designed by the same design groups, you're going to see this merger, if you will, of the best attributes of each one of those material systems. And you're really going to start to see compound semi materials and all the advantages of frequency and power and light emission combined with all the strengths of silicon, light and signal processing, data and signal processing and things of that sort to just create a new class of merged CS and silicon functionality. It's really exciting for the future.
Well, thank you very much, Wang, for discussing the RF semiconductor market trends and new technologies that are being enabled by epi materials. We really appreciate your insights, and I want to let everyone know you can find more videos at videos.microwavejournal.com. Thank you for watching, and join us next time on Frequency Matters.